Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to go over problems 6 to 10 of the Geometry Regents exam for January 2015. All right, let's take a look at problem number 6. It reads, what are the truth values of the statement opposite angles of a trapezoid are always congruent and its negation? One thing you want to note about this problem is that the negation of a statement involves changing is or are, as in the case of this statement, into is not or are not. Okay? And secondly, you also want to note that if a statement is false, then its negation, which is the opposite of false, is automatically true. Okay? And if a statement is true, then its negation is false. Truth values basically represents all the states of the all the states of the possible cases of a statement. Is it true or is it false? If it's always true, then that statement is true, and if all the truth values are always false, then that statement is false. Okay. Now, the steps we are going to use are as follows. First of all, if we can find one counter example for a statement, then that statement is automatically false. Okay? For example, if someone makes a statement that all humans are on Earth, all you need to show, all you need to do to show that that statement is false is to find someone that's not on Earth. Let's say someone is on the moon or someone is on Mars, and you say, but there exists a human that is on Mars, and Mars is not the Earth. So that's a counterexample. Just only one counterexample is sufficient to show that a statement is false. Now, if you can find no counterexamples, then you have to use a rigorous proof to show that all cases are true. All right, so first thing we're going to do is we're going to look at this statement, opposite angles of a trapezoid, look at all the possible configurations of a trapezoid, and ask ourselves, are the opposite angles always congruent? We'll look at the truth values there. If they're always true, then the statement will be true, and its negation will be false. But if we can find one counterexample, a case where the opposite angle of a trapezoid is not congruent, then that statement is automatically false, and its negation, the opposite, will be true. Okay? Now let's go ahead and draw a trapezoid. Remember, a trapezoid is a quadrilateral with at least one pair of parallel sides. Okay, so a parallelogram is a trapezoid too, but I'm not going to draw a parallelogram here because it's not going to give me a counterexample. What I'm looking for is a counterexample. All right, so take a look at this trapezoid right here. Let's call this trapezoid A, B, C, D. Now, the truth values of this statement will always be true if any pair of opposite angles I pick in this trapezoid yields congruent angles. Okay, if that's not the case, we have a counterexample. Now let's consider angle B and D. Are they congruent? Well, let's write this down from trapezoid ABCD. Okay, angle B is opposite angle D, but note, but angle B is not congruent. Angle B is not congruent to angle D. What do we have here? We have a counterexample to the original statement, which says that um, opposite angles of a trapezoid are always, that means all of them. Well, we have one case that's not. So this one case we have here is a counterexample. Okay, this is a counterexample. And if you can produce a counterexample to a statement, then that automatically means that the statement is false. Okay, So the statement is false. All right, that's all you need to do. Now that we've shown that the statement is false, it automatically follows that the negation is true. Okay, let's write that down. Since the statement is false, its negation must be true. Okay, its negation must be true. So what is the negation of this statement? The problem doesn't ask you for it, but let's just go over that just as a good review. So the statement is that opposite opposite angles of a trapezoid are always let me go back to it. Opposite angles of a trapezoid are always congruent. Okay, yeah, are always congruent. Always congruent. Okay, so what's the negation here? Just for practice, we already know what the answer is. Here, the statement is false and the negation is true. So the answer should be, let's see what the answer is. Statement is false, negation is true. Statement false, negation true. Answer is option number 3. But let me just show you what the negation looks like. So the negation, you're just going to write the statement as opposite opposite angles of a trapezoid. Now this is where you change. Instead of are always, what do you write? Are not. Okay, if it were is, you say is not. Are not. That's how you achieve the negation. Okay, are not always congruent. And we can completely see why this is the case because we have an example here that shows that they're not always congruent. They could be congruent in the case of a square or parallelogram, um, but if you have a trapezoid of this case, or even an isosceles trapezoid, then the statement is not true. Okay, so opposite angles of a trapezoid are not always true or are not always congruent is a true statement. That is a negation of the original statement. Opposite angles of a trapezoid are always congruent, which is false. All right, so that's that. All right, let's take a look at problem number 7. It says, what is the length of a line segment whose endpoints have coordinates 5, 3, and 1, 6? So one thing you want to note is that when you're using the distance formula, it's very easy to accidentally interchange coordinate values. So you want to label, label, label. All right? All right, these are the steps we're going to be using for our problem solving process. We are going to first write down the distance formula, and then we're going to label our coordinates so we know what's going where. We substitute it into the distance formula and evaluate the value of the distance. Okay? All right, so let's go ahead and start with step number 1, which is to write down the formula. So the distance formula, it's from the Pythagorean theorem, just applying the Pythagorean theorem to coordinate geometry. So the distance between 2 points P1, P2 on the two-dimensional coordinate plane is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay? So you're going to make sure that your x's are together and your y's are together. Very easy to interchange things. All right, so there goes our formula. Next thing we're going to do is we'll advance to step 2 where we'll label our points, um, label our coordinates. So let's call the first point P1, okay? So P1, the first point, that's 5, 3. Let's see, what do we do here? Let's call the x coordinate x1. So x1 is 5 and y1 is 3. So we have the x1 and the y1 in the distance formula. Okay, now we need the 2's. Let's call the second point P2, 1, 6. So this means that x2 is 1 and y2 is 6. All right, what do we have now? We have all the ingredients to compute the distance between P1 and P2, right? So let's go ahead and substitute these values into our distance formula. So the distance between P1 and P2 is equal to the square root of x2 minus x1, 1 minus 5 quantity squared, plus y2 minus y1, 6 minus 3 quantity squared. Okay, and then we take the square root of the entire expression. Now, let's go ahead and simplify this using the order of operations. So we're going to have the square root. 1 minus 5 is negative 4 square plus 6 minus 3 is 3 quantity square. Simplify that further. Negative 4 square. Now be careful when you square negative is positive. Okay, so negative 4 square is 16 plus 3 square, which is 9. Take the square root of the sum. That equals square root of 25, and then that's 5. So what did we just find? This is the distance between points 1 and 2, between 5, 3 and 1, 6. Our answer is option number 1. All right, let's take a look at problem number 8. It says, in the diagram below of isosceles triangle ABC, the measures of vertex angle B is 80 degrees. If AC extends to point D, what is the measure of angle BCD? So we're looking for the measure of this angle right here. Okay? All right, so first thing you want to note is that by definition, an isosceles triangle is a triangle with a pair of congruent sides as illustrated here. We have one tick mark here. That means these two sides, AB and CD, are congruent. And that follows that there's also a pair of congruent angles. The two angles that are opposite those two congruent sides are congruent. So the angle opposite BC, angle A, is congruent to the angle opposite AB, angle BCA. Okay? So isosceles triangles always have one pair of congruent sides and one pair of congruent angles. All right, now steps. First thing we're going to do is we're going to find the values of these two congruent angles here. Secondly, we are going to use the value of one of the congruent base angles to determine the angle of the value of angle BCD. Okay? All right, so let's start by focusing our attention on angle B, ABC, and using its isosceles nature to determine the measure of the base angles. Okay? So, step one, since triangle ABC is isosceles, what do we know? We know that BA is congruent to BC. That's a given fact. Okay? Now, this follows that the sides that are opposite the congruent sides, the angles that are opposite the congruent sides are congruent. So the measure of angle A is equal to the measure of angle BCA, right? Since um since they are opposite the congruent sides. All right, now with that in mind, we can use this fact to set up an equation. Using the triangle angle sum theorem, we can set up the following equation. Measure of angle A plus measure of angle B plus measure of angle BCA is equal to 180 degrees using the triangle angle sum theorem. Angle sum theorem. All right, now let me make a quick notation here. Let's call this equation A. All right, because I'm going to be using it momentarily. Okay, so now we have this right here. Um, Since measure of angle A is equal to measure of angle BCA, I can make a substitution. Wherever there's angle A, I could use BCA. Wherever there's measure of angle BCA, I can use measure of angle A. So I can use it interchangeably. Now, since BCA is what I will be using to find BCD, it's adjacent to BCD, I will like to substitute A with BCA using equation A. Okay, so let's go ahead and make that substitution. Measure, let's change the color there. Measure of angle, instead of A, measure of angle BCA, okay, plus measure of angle B. What do we know the measure of angle B is? It's 80 degrees. So let's just put in its angular value, plus 80 plus measure of angle BCA is equal to 180 degrees. This is by substitution. Okay, I made a substitution of what angle A is equal to into this equation right here. Now we're just going to use algebra to find the measure of angle BCA. Since these are like terms, we can combine them into one. We're going to have a measure of angle BCA is just like x plus x, okay? Plus 80 is equal to 180. And then we're going to subtract 80 from both sides. Subtract 80, and then we'll get twice the measure of angle BCA is equal to 100 degrees. Now, how do we get measure of angle BCA by itself? We simply divide by 2, right? So you divide this by 2, divide this side by 2, and that yields the measure of angle BCA, which is what? 100 over 2, 50 degrees. Okay, so let's go ahead and populate our triangle with the numerical result we just got. This is 50 degrees. What is this right here? It's 50 degrees also because this is an isosceles triangle and base angles are the same. Now we're going to use this angle to find measure of angle BCD as indicated in step number 2. Okay, so let's go to step 2. Step 2, we know that the measure of angle BCA, okay, measure of angle BCA plus the measure of angle BCD is equal to 180 degrees. Now, do you know what the reason why we can draw that conclusion? Why can we say that the measure of angle BCA plus the measure of angle BCD is 180 degrees? We can say that because these two angles form a linear pair. They are supplementary, okay? They form a linear pair. Okay, so by substitution, we know that measure of angle BCA is 50 degrees, so we can substitute that value here. 50 plus the measure of angle BCD is equal to 180. That's by substitution. Okay, and then from here on out, we just use algebra to isolate measure of angle BCD, and that will be our final result. All right, so let's go ahead and isolate that by subtracting 50 from both sides of our equation. So that yields the measure of angle BCD is equal to 130 degrees. Okay, answer is option number 4. All right, let's take a look at problem number 9. It says a student uses a compass and a straight edge to construct CE in triangle ABC as shown below. So initially all that the student had was just this triangle ABC. So they basically did a construction and it resulted in the creation of segment CE. Okay, the line through CE. Okay. Now the question is, what statement must always be true for this construction? Now, one thing you want to note is that when you bisect an angle, you're basically dividing the angle into two congruent halves. Okay, that's the meaning of bisection, is to split it into two equal halves, two angles that are congruent to one another. Now let's go over the steps that resulted in the construction of segment CE. So when you're bisecting an angle, first thing you do is you just draw arc. So first thing he did is he drew this arc right here. Okay, so that's step one. He drew the arc. Now, without changing the length, without changing the measure of his compass, he placed the tip here and then drew this arc. All right, and then put the pointy tip of the compass here, and then he drew the second arc right there. Okay, so they intersected at this point. And then he proceeded to draw this line through this intersection right here. Okay, so what he did is he basically bisected this angle. This angle right here is congruent to that angle right there. That is the procedure for bisecting angles. Now, if these two angles are congruent, what statement can we make? If this angle and this angle are congruent, what statement can we make? We can simply conclude that angle ACE is congruent to angle um, BCE, right? So let's go ahead and write that down. Since it's a bisection, um, since CE, segment CE bisects um, angle ACB. Bisect means it's split it into two equal halves. That follows that angle ACE is congruent to angle BCE. Answer is option number 2. Okay? All right, let's take a look at problem number 10. It says in triangle ABC, AB is equal to 4, BC is 7, and AC equals 10. Which statement is true? So which of the statements is true? Now, one thing you want to note is that in a triangle, as you increase the length of a side, what happens is that the measure of the angle opposite it starts to get bigger. Okay, and then as you shrink the measure of the length of a side, the measure of the angle opposite it shrinks also. Okay, so there's like a direct um, uh, relationship. They vary directly with one another. Okay, a direct variation. Now, these are the steps we're going to use to solve this problem. We are going to sketch and label the triangle completely. Now, this is very important so you can keep track of which angle is opposite which side. Very important to give yourself a visual, a concrete representation of the situation. After sketching the triangle, we are going to use the order of the sides of the side lengths to order our angles, the opposite angles accordingly. Okay, because it follows the same order. If you order the side lengths from biggest to smallest, then you will be ordering the opposite angles from biggest to smallest. So let's go ahead and just sketch our triangle. This is going to be a scaling triangle because you notice that no two side lengths are congruent. So we just want to follow that pattern there. All right, so let's see. Let's label it AB is the smallest. So in this triangle right here, I'm going to make AB the smallest. So AB is 4. followed by BC, which is 7, AC is 10. Okay? So what do you notice about the order of the side lengths? This is the longest, followed by this side, and then that side. Okay, so let's go ahead and write it down. Now, since AC, the length of segment AC is greater than the length of segment BC, and the length of segment BC is greater than the length of segment AB. Since this is the case, and segment AC is opposite angle B, and segment BC, I'm following the order here. AC first is opposite angle B. BC, side length BC, segment BC is opposite angle A. And AB, the shortest side, is opposite angle C. Then what follows? It follows that these angles that are opposite this side follow the same order of magnitude, okay? So since AC is the biggest, the side opposite it is, the angle opposite it is going to be the biggest. So measure of angle B is the greatest, is going to be greater than, since BC is greater than AB, then angle A has to be greater than angle C. And they're both less than B, of course. So measure of angle A is greater than measure of angle C, because BC, the side opposite A, is greater than AB, the side opposite C. Okay, so what you see here is that just by ordering the sides, so this is 1, 2, 3. Just by ordering it like that, we can automatically order the angle. So this would be 1, since it's opposite that one. This would be 2, and then that would be 3. And then going from 1 to 3, you're going from biggest to smallest. So go 1, 2, 3. B, A, C, from biggest to smallest. And that's the order of the size of the angles. All right, so let's see which one is correct. Measure of B is less than measure of is greater, I'm sorry. Measure of B is greater than A is greater than C. Answer is option number 2. Thanks so much for taking the time to watch this presentation. Really appreciate it. We'll also like your feedback on this clip. If you like this presentation, we'll appreciate it if you give us a thumbs up, so that we'll know that you found this presentation helpful. If you have any questions, please place the question in the comment section below, and we'll be glad to address it as soon as possible. And do not forget to subscribe to our channel, okay? Have constant updates to the remainder of this review series, and if you subscribe to our channel, you get instant notification of the updates. Thanks again for watching, and have a wonderful day.